So that's it. It's way lower than that.
Hello and welcome back to Calculus 3. We are continuing our exploration of chapter 14, and today we have line integrals. So what do line integrals compute? Well, they compute area. Now, the interesting thing is they are able to compute the area that is not a flat surface. So if you observe a curtain that hangs, you know, right, that it waves. It's not a straight rectangle. Now, yes, you can take this curtain off the wall. You can straighten the curtain into a rectangle and measure its area. That's great. But what would you do if you are not able to straighten the curtain? If it's made out of some material that you can't flatten, if you try, it breaks. Let's say you have a glass curtain, right? So glass curtain you can make flat. So we have the idea of having, so in the 3D space, we have some kind of a line. We call that line C. That line is in the XY plane. And then from that line, we have the curtain going up, and then we have some whatever kind of top that is governed by Z equals fxy. The area of this curtain is going to be given by the integral over the curve C of the function f, and then we parametricize this with the arc length. Arc length in the for the line C. We are going to use parametric equation, convert this ds into dt. We have seen that before. So we are looking for the area of the curtain, and this gives us ability to find the area of uneven surfaces, okay? If we are able to pinpoint the line C and which way the line C works. So that's what we have. The image in the book that you looked at before, it's pretty much the same thing. You see that the blue surface is given by z equals fxy, and this red line is the line of the curtain that touches the top of the blue function. So your top on a curtain is a straight line, right? Because you have the rod from which it hangs, and that's a straight, right? But you can make interesting stuff, right? The rod doesn't have to be straight, right? The rod can be bent, and then you can have the curtain on top be whatever, right, shape. So that would be the red line. And then you have the area of the curtain, which is the gray stuff, right? In my case over here, I shaded a red. And then you have the black line on the bottom, which was the curve C, and that's the curve over which we get to integrate. So we pick the small parts on the curve C, and because it's a curve C, each little part of the curve C would be the arc length. So we say it's parametricized over arc length. So the line, the curve C, is broken not into small dx pieces, but it's broken into small ds pieces. S stands for arc length. Now, this is obviously only important to derive the equation, and we have a definition for a scalar line integral in the plane, which is, again, the honors part for the course. So suppose the scalar valued function f, that's f of xy, right, is defined on a smooth curve C. Now, the word smooth means it's differentiable, it's continuous, and so on. C, which is given as vector r of s, which is parametricized as x of s and y of s, we are going to turn all of these into t's that we know from before. So parametricized the line integral of f over curve C is, and this is the formal definition, so integral C of f parametricized x and a y and s ds is equal to the standard Riemann stuff, right? So limit delta goes to 0, e goes from 1 sum e to 1 to n, f of xs star ys star, and then delta s. Oh, there are k's over here, I forgot. So this is the definition. It's the standard Riemann integral that we are used to. This is k equals to 1 and whatever. The line C has the little patches. They don't have to be the same length. Each one of these is sk. That gives rise to the area that is over here. That looks like pi. No matter which way it's going to look like pi. So I'll add another one. So this one over here is your f of xy, and we are calculating the area of one of these rectangles. Now that rectangle is going to be curved because it's sk, the arc length on the bottom is curved. Now this is not the way to compute things. The book does show a few examples on how to compute with the arc length as a parameter, but it's much better if we just go with our standard parametrization in respect to t, the one that you know, that the circle is parametricized as cosine t sine r, cosine t r sine t, and all of that stuff. So immediately, big theorem on how to compute line integrals. So evaluating line integrals. So the first one is so let f be continuous on C, and C needs to be given by your good old vector valued function R, which contains your parameters x of t and y of t. These are your friends from chapter 11, all the way from chapter 11. For t being trapped between a and b, those are your limits of integration. Then your integral over c of f ds is going to be given as the integral a to b f in terms of the parameter x of t, y of t, and this is the extra piece now, absolute value of, it's the magnitude of the derivative vector dt. So when you convert from the arc parameter, right, the parametrization by arc length into the parametrization by parameter t, you'll gain the extra term in there. And that term, guys, is the also known as the velocity vector, right? So you can you can, if you want to, here, I'll do it in blue. Over here, you can call this absolute v of t, right? Which is speed, right? So that's what it is. We get to box this because this is our way to compute line integrals. Not efficient way. We are going to learn Green's theorem for certain cases, and so the next two sections are quality of life improvements on this, right? Because sometimes this thing can take forever. So to evaluate line integral, first order of business is to parametricize curve C and then express your function f in terms of those parametric equations, and then go and deal with everything else. So that would be the procedure. Maybe I can write the procedure here. So number one, parametricize C to express f x y in terms of x of t, y of t. 3. Compute speed. 4. Plug in. 5. Win. There you go. That's your steps. You can replace word win with profit, whatever. I don't know. It's the end of the problem. Now let's take a look at an example of this. And then we have successfully completed 20% of the lecture. Holy nightmare, I forgot there's like 15 pages in here. There we go. So, problem 16 says to compute the line integral C for x squared plus y squared ds, where C is a line segment from 0, 0 to 5, 5. So this is what we have. All right, so to compute this line integral, we have a straight line. Yay! We need to write a parametric equation for this. We have what should we do? Y equals x, because 0, 0, and 5, 5. Very good. So y equals x. Now, these are not parametric equations. This is the common sense equation from algebra. That's very good. So now, how do I turn this into parametric equation? So the important step of y equal x is done. Now, how do I turn this into parametric equation? Remember what I need. I need r of t is equal to some kind of a vector, and then t trapped between two values. So this is what I need to get. That's the parametrization. And this is your chapter 10. Yes, ma'am. That would be if it was a circle. This is a straight line. So cosine t sine t would be if it was a unit circle. Right? 1 and 1. Then it's cosine t sine t. We have a straight line. That could be the answer, but then it's going to be, that's one of the ways. Can we just do t and then go from 0 to 5? You want to go from 0 to 1, right? That's why you said 5t, 5t. All right, so the suggestion is to go 5t and 5t, which is fine. You can. In which case, your t's would be 0 to 1. You can also go t and t, and then go from 0 to 5 on t. It really doesn't matter which way you go. Now, trying to make this as easy as possible, because you have to use this to compute speed. So it is easier if we just use t and t than 5 and 5, because we still have to take the derivative and then do the absolute value of that. So you are looking for the easiest possible way to set these equations here so that the future calculations are also easier. So I'm going to switch back to t and t, but I want to say that 5t and 5t is perfectly fine, except it's going to be a little bit more involved later to compute things if you have the derivative. So instead of having 1 and 1, you're going to have 5 and 5. It's obviously not a problem. So we have now the derivative of this to be 1 and 1. And the magnitude of that derivative, which we call velocity, right, would be square root of 2. So I have all of the pieces that I need. I will go, oh, now I see why you said sine and cosine, because you've seen the equation of the circle in here. Okay, that's f. So this has nothing to do with parametrization, guys. This is the function f, and once we have parametrization, then you are going to change those guys in terms of that parametrization. The line C, or what you are parametricizing, is given on the side. Okay, now I understand why you went for the unit circle. So now I have integral 0 to 5, that's from the limits of t to get the line segment from 0, 0 to 5, 5. Then I have x squared. Well, x is t, so I have t squared plus another t squared. And then I have the speed, which is root 2, and then I have dt. Kick 2 root 2 outside. We are integrating t squared dt. Right, t squared plus t squared is 2t squared. So 2 root 2 I'm kicking outside. Now I have 2 root 2 times t cubed over 3, computed from 0 to 5, is going to give me 2 root 2 over 3, and then I have 125 over here minus 0. So this is 250 root 2 over 3. 2 plus 5 is 7, not divisible by 3, so leave it as is. And that's the answer. So this would be the area of the curtain. That would be the area of the curtain. And this is actually the this curtain is on the bottom straight line, because that line goes from 0, 0 to 5, 5, right? Yes, it goes diagonal, right, on the xy plane, but if you rotate the space 45 degrees, it would just be a straight line with a 5 square root of 2 length. And then these walls are straight. The top is not straight because of the function f. So we found that the shape of that curtain that created. Now this curtain is flat, right? It's just that the top was not flat. Let's see one more example where we do the same thing now in a 3D space. So line integral, now we do the line integral in 3D. So line integral in R3. It's the same thing. Looks exactly the same. I'm going to write the formula here. We have our integral C f ds is going to be now integral a to b. Your f is now parameter x of t, y of t, z of t. Still times the velocity, absolute value of the magnitude of velocity, and then dt. As you can see, this formula is different than the previous one. I just have z. Now you guys also know that z will be the part of velocity as well. So you're adding two components in, actually. Let's see. I want to integrate over something interesting. They have circles. Good. 26. So we are integrating x minus y plus 2z ds, and the c is given as vector r of t. Now this is already parametricized for you. 1, 3 cosine t, 3 sine t, where t is between 0 and 2 pi, we're parametricized over the entire circle. Guys, this is a circle. You might be going, wait, that's a helix. No, it's not. There's one. Helix has to have a variable there so it can progress in a third dimension. Your two dimensions over here, 3 cosine 3 and 3 sine t, those are fixed to be a circle. And then if you want that circle to extend in a third dimension, you have to have a variable that will take it there. If it's just a value, that just moves the circle, the ring, right? You can think of a ring, right? So I can have that ring sit on the floor, and then it's 0 on the first. I can have that ring on a desk, then it's 3. I can have this ring taped for the ceiling, and then it's 10. So if I have this as a value, it just shows me where this, so this ring is 1 foot off of the floor. That's all it is. And if I put a t over here, then it becomes a uniform spiral, which is a helix. So you have to be careful about that. There is a helix problem. 29 is a helix problem. They have 3 cosine t, 3 sine t, and then t. That's the helix. This is just a circle. Parametrization is already done for us, so we don't have to do any of this work over here, right? All I need to do is to go get the derivative, get the velocity. So r prime, which is the velocity vector, is going to be 0, negative 3 sine t, 3 cosine t, and then absolute value of that velocity would be the square root of 0 squared plus negative 3 sine t squared plus 3 cosine t squared, and that's going to give us altogether 3, because 9, you factor out 9, sine squared plus cosine squared is 1, you have 0 plus 9 is 9, square root of 9 is 3. So all I need to do now is to put this calculation together. The line integral is, let me just separate this, I have integral from 0 to 2 pi, those are the limits on t that are given to us. For a full circle, obviously 0 to 2 pi. Now, x is given as 1, minus y is given as 3 cosine t, plus 2 times sine t, so that's 6 sine t. Then we have times 3, which is velocity, and finally dt. So once you get all of the pieces of the puzzle, you just plug them in. X for x, y for y, z for z, and then velocity, absolute value of velocity goes there. Now I have the integral 0 to 2 pi, and I have, we can kick 3 outside of the integral, obviously, and now we're integrating. I have t, oh wait, I put the integral, no, I need to, sorry, no integral there, I'm integrating. So t minus 3 sine t minus 6 cosine t from 0 to 2 pi. That's going to be 3. Now, when I plug in 2 pi, I get 2 pi, sine dies for both 2 pi and 0. Cosine t becomes negative 6, because cosine of 2 pi is 1. Then we have 0, that's dead, sine is dead, and the other one is minus, so that's going to be plus 6, so the whole thing is 6 pi. Ta-da! So that's the way we compute line integrals. Your job is to go and figure out parametrization, and once you have parametrization, you go and plug everything in. Don't forget to compute the velocity. Now, I'll write this as, put it in green. I haven't put stuff in green. To compute length with line integral, you compute the line integral without function f. Okay? So, we can calculate length using, good effort, line c of ds, which would give us the integral a to b, no function in there, you just have the velocity vector in terms of t dt. So to calculate the length, so if you have this wavy line of the curtain on the bottom, you can calculate the length of that line. If you calculate the line integral with the function, you are calculating the area of the curtain. If you kick the function out, you are calculating the length of the line on the bottom of the curtain. They should have few problems for that in the back. We can calculate one and then continue with the other 60% of the lecture. This is 15 pages in the book. Like, one thing they could have broken into 2 sections, they haven't. But then they have an entire chapter on power series, which they really didn't need to. Anyway. Length of curves. They have two full problems for this. Great. Helix. Length of the helix. That's cool. And the length of the slinky. Those are the two. You know what the slinky is, right? We talked about slinky. We know that that's the helix that you connect, right? You take a spring and you connect it. So you have a donut shape, but it's actually a spiral. So that's a slinky, right? So we can do either a slinky or we can do the the helix. Let's do Slinky. It's harder. It's crazier. So problem 32, the parametrization for a Slinky. Guys, this is the conversation starter next time you talk to someone, right? When they have that, like you see a kid playing with it, sit it down next to you, explain the parametric equation for it. It's a very simple concept. No? 30 sine t, 40 sine t, and 50 cosine t. T is between 0 and 2 pi. Our job is to calculate the line integral without a function. Function is not given to us, right? That we see that. So we're only calculating the length of the line. The way we do that would be the C ds, which is the integral a. Well, I have it up there. Yeah, it's showing. So all I need to do is to calculate r prime, which is velocity. So I'll calculate the velocity as the derivative of r, in respect to t. So derivative of sine is cosine. So we have 30 cosine t, 40 cosine t, and negative 50 sine t. And then we have to integrate 0 to 2 pi. And then I have over here the magnitude of this. So it's going to be a square root of 900 cosine t, cosine squared t, plus 1600 cosine squared t, plus 2500 sine squared t, minus dies in the process of squaring, 0 to 2 pi, square root of, when you add the two cosine squares, you get 2500, right? This is where you go, right? Otherwise, elliptical, and then good luck. Another, 5 years of math, or 6 years of math before you get to solve it. Sine squared t dt. Kick out 50 in front of the integral, which is the square root, right, of 25, which factor. So that's 50 in front of the square root of 1 dt. So the answer is 100 pi. So if the kid asks, what's the length of the line for the Slinky? It's going to be a circle with additional term that would add into elliptical, which is not easy to compute. So what you have to do in order to answer that question is you have to squish that Slinky into an ellipse first a little bit, right? And then when that is an ellipse, then the terms are going to add into a circle later on, so, right? That's important. So that's the way to compute the length of the line. Great, 40% over. Let's go. See if we can get halfway through the lecture. Good effort. Now, line integrals can be computed in vector fields. We covered vector fields yesterday. So vector field is a function that assigns a vector to each point in space. How many points do we have in this space? Infinitely many, right? In this room, we have infinitely many points, right, in this space. So now if there is a wind blowing through the room, let's say air conditioning kicks in up there, right? It's going to spew the vectors all the way right through the classroom. At each point in space, there is going to be a vector which pushes the molecule of air in that particular direction. So we can see, very easily you can see the vector field. If you are ever sitting dead still in a house, right, and just you observe like small specks of dust moving in a sunlight, right, they're moving according to the vector field. They're being pushed in the vector field of your house, in the room. So now we can calculate the vector field because, again, what is the line integral? It's the function times the velocity vector dt. What is a vector field? A vector field is a function that assigns the vector to a point. So all I'm going to do now is I'm going to replace the function on top of the that gives me a surface that it's hard. I'm going to replace that function with the vector field function, and instead of times, I will use the dot product, because times is the dot product, right? It's just a one-dimensional dot product. Actually, the only thing that exists is the dot product, and then your 3 times 15 is a dot product between two one-dimensional vectors. Those one-dimensional vectors only have magnitude 3 and 5, and when you do the dot product between them, you get 15. Now, when you move to 2D, 3D, 5D, 16D, whatever you get, then you have to do the multiplication of each component and add them up. So now, I'm just going to move from one-dimensional multiplication to 2 or 3-dimensional multiplication, where I'm replacing your function, which was a scalar, one function, with a vector function called a vector field. And now, in the vector field, we are going to have the line integral computed with the vector field f dotted with r prime, your velocity. So now its velocity is not speed, right? The dt. And we have a few forms. For this, obviously, only one of these is for calculation, and the others are for the show. Right. So here are all three. So A, B, the dot product. Remember, well, I'll write it. What the hell? All right, so let's write it over here. First, vector field F from last lecture. Vector field F had f of t, g of t, and h of t as functions. And your R had x of t, y of t, and z of t as components, and that's from chapter 11. So now I have the dot product of these, which means multiply the first two, plus multiply the second two, plus multiply the third pair, right? So, here we go. The dot product between f of t, x of t, but x of t is prime because we need the derivative of it, plus g of t, y prime of t, plus h of t, z of t prime, and dt at the end. So that's that. And now we have the funny notations, right? The ones that you would leave on the napkin behind as you leave the places, right? Integral over c, and that's going to be f dx plus g dy plus h dz, which can further be collapsed into f dr. Now note the vector notation on that r. It's not there for decoration. That's your dx, dy, dz dot product. Now, when I took Calc3, that's the only equation I remember, because I know what these things mean, and I can write this out. If you spend time to learn that R is what it is, and then you know that dr is the derivative of that, you can get your x prime, y prime, and z prime directly knowing that your r is x, y, z, and then dr is the derivative, so dx, dy, dz. So it brings you here, and then that jumps one back. What happened between these? Guys, what is x prime? It's dx, dt, dy, dt, dz, dt, over dt in each one of these, factor out, cancel. You see that? One more time? Sure. It's dx dt, dy dt, dz dt, so each one has over dt, factor out dt and cancel, and that's this. And then the dot product fgh, that's fgh, that's f, and then dx, dy, dz, fdr. Multiply through with dt over dt, it expands into this formula on top. So, again, this is usually where hell breaks loose in this class. The first time I mentioned the vector field in the line integral, half of the classroom checks out. I don't know what's happening. All that's happening now is I replace the good old function that you are familiar with. When I take this and I create a shape, this shape on top is given by some function f of x and a y, or f, x, y, z. And you're all familiar with that because we've been talking about an entire semester, right? Now, I'm going to take that away, and I'm going to put a vector field instead of it, because vector field is a function. Now, see, the problem is that if you don't learn the definition of the vector field, right, you pretty much have an idea of what vector field does. Great. But you have to know that its definition is that the vector field is a function. That's the first thing I said. Look at it. A vector field is a function. Done. So if I have a line integral, and the line integral is over a function, I'm going to take the scalar function away and put a vector function in. It doesn't matter what kind of function you have. The whole idea of the line integral is a function times arc length, or a function times velocity times the dt, if you want to get out of the arc length business. So now with this, playing the game of calculating the vector field equations is a lot of mathematical gymnastics, right? Because we have to parametricize C, that gives us R, then we need R prime, then we have to put all of that stuff in the vector field, and in the vector field they can be in any order they appear. And then after, being expression being like 2 lines in your notebook landscape, you can finally start clearing out the algebra and calculating things. So yay, let's take a look at that. And then you get the physics problem to calculate work or something. Let's see, what do we have? We are going to do a vanilla problem first, and then we're going to take a look at something more menacing. So how about first start with something as nice as, let's say, 35. We have a vector field given as yx. Our curve C, line segment from 1, 1 to 5, 10. Great. we are supposed to calculate the line integral for it. All right. What do I need to do? Well, parametrization is the first thing we have to do. Let's go orange. Parametrization. So I have 2 points in space, and I have to hit the line through those, and then we have to deal with the rest. So I have my slope m to be 10 minus 1 over 5 minus 1, which gives me 9 over 4. Now I have to use a point, let's say 1, 1, to compute the b. So 1 is equal to 9 over 4 times 1 plus b. So b is equal to 1 minus 9 over 4, which is negative 5 over 4. And I have my equation y equals 9 over 4x minus 5 over 4. So this was your elementary algebra to find the equation of the line having 2 points. The next order of business is for us to come up with a parametric equation that would make our r and our r of t, right? So the easiest way to achieve that is always to say x equals t, and then y equals whatever equation is there right now in terms of t. That's the fastest way to do parametrization. Is it the best way? Obviously not, right? Obviously not. What would be the better way? Well, maybe if you have t over 4, right? No. Is it t over 4 or 4t? I can't think now. Let's see. If I say x equals 4t, and then I plug 4t in here, nah, it's not going to make it better, because the 5 over 4 will stay. Such is life. Good effort over there. Because it will remove on the 9 quarters, but 5 quarters will stay. So whatever. Here we go. So now r of t is given as t, comma, 9 quarters t minus 5 quarters. Giving us that our r prime of t is 1 and 9 quarters. Bueno? So, look what we have, guys. We have our r prime, and that is this guy and this guy. We don't need this guy because we're on a 2D now, right? R2. So we have these two. The only thing I need is f and g to plug in, and we're done. So let's go and write that out. My formula over here, nice. It might come back, it might not come back, so just listen. No, fine. You're lucky. So the integral that we are computing from, I didn't say a to b. So what are my limits? See, I completely, so these are the parametric equations, and now I need my t between two values so that we can get to 1, 1. So if t is equal to 1, right, we start, because x equals 1, and then y would equal 1. Now, what is my other side? It's 5, right? Because 5, you plug in 5, that's a 5. Plug in 5, that's a 45 minus, yep, 40 over 4, 10. Good. Don't forget this piece. Well, you'll remember it when you have to put the limits and you don't have them. Here they are, 1 and 5. Okay, what do I have? I need f times x prime plus g times y prime dt. And this is where mathematical gymnastics start. Guys, this is your x and of t, and this is your y of t. When you go to the vector function that it's given to you, your vector function f is given as yx. This is your f, and this is your g. So you have to look at the 3 locations at the same time. If that doesn't make it cross-eyed, nothing will. Your f is supposed to be y, and your y is this thing. So that goes for f. Cool? One more time. Your formula is f x prime. So f needs to go there. Well, f is y, and y is this. That's why I said you have to look at 3 places at one time and then write it in the 4th spot. So this becomes now integral 1 to 5, one more time, f, which is y, in this case, which is this. Yay. So 9 over 4 t minus 5/4 times 1. That's here. I'll let you one more time follow that. This is what detectives do all day long. All right, now we go for the next one. So the next part that I need is g. G is this guy, which is x, which is this. Guy, that vector field could have been y comma y, right? Y comma y. In which case you will be using this twice. Could be anything. You know that the vector field can be anything. So you have to carefully chase what goes where. So that will give us plus t times 9/4. And then all of that dt. Now we have the simplest possible Calc 1 integral to compute. 1 to 5. We have 9/4 t minus 5/4, that's all times 1, plus 9/4 t dt. This is 9/2, so we have integral 1 to 5 of 9/2 t minus 5/4 dt. Integral of this is going to be 9/4 t squared minus 5/4 t, computed from 1 to 5. This is 9 times 25 over 4 minus 25 over 4 minus 9 over 4 plus 5 over 4. This is 8 times 25 over 4, because 9 apples minus 1 apple is 8 apples. And then this cancels. Minus 4/4. and I have 50 minus 1 is 49. Yay. The only thing you're not used to is probably that quick computing trick where I said 9 apples minus 1 apple is 8 apples. I factored rather than actually multiply and subtract. Because algebra, right? Over here we have negative 9 plus 5, that's negative 4. And that's it. I love that I spent some time doing arithmetic, explaining arithmetic rather than, working on the line integrals. But believe it or not, that's needed more in today's day, right? Because you start with calculators and you just don't know any of the cool calculation techniques. I mentioned physics. Why would physics be important? Well, you want your fridge magnets to stick? Exactly. I can't live without that one. So, magnetic field and electric field are fields that have vector field equations. Everything we have on this planet depends on it. Well, first off, you have a magnetic field of the planet. The reason why we are alive. That's number one. The number two, obviously, is all of our technology. I already mentioned in this class that 100% of our technology depends on an electrical motor. You get to produce nothing other than paintings and pieces of art without electrical motor. It drives all of our technologies to build everything we have. Well, that's electric and magnetic fields right there. So, in order for any work to be done at the state we are in as a civilization, which is still type 0, i.e. pathetic, yeah, you think you're cool because you have the cell phones and stuff. It's just insignificant. Every single one of us. In comparison to not even the insignificant even in the planet, we can't even control the climate of the planet yet. Type 1 civilization can control climate of the planet. We can't do that. Now you have type 1, type 2, type 3, type 4 civilizations. You know what that means? Galactic empire. We are nowhere. We can't even go back to the moon because Congress says, right? That's that. So we have fields, and to do the work in a field, whether it's magnetic, gravitational, electric, nuclear, whatever, right? We have the line integral for the magnetic field, so work is equal to the line integral because the work is done in line. If I am pushing a fridge or a couch or a chair, right, that's going to be done along some kind of a line. And the work is the collective effort, the sum of all forces over the distance that has been pushed. So work is going to be given as the integral over curve C, the vector field times r prime. Again, remember the parametrization. We are not learning new mathematics here. This is just application for work. So with this equation now, you have a rotational magnetic field. Rotational magnetic field is given to you by the field we talked about earlier last class. You know what the rotational field looks like, negative y, x. So when you have a rotational field, right, you are going to dot that with r prime, which is the velocity, right? And you get the work done in that field. So in the design of electrical, you want to be electrical engineering. You want to design the new motors. So Volkswagen is investing an insane amount of money now into electric car development and the batteries development. They're going to put, I think they invested like $4 billion into this thing. So they're going to build apparently 5 gigafactories. You know, Elon Musk has 1. These guys are going to build 5. See, Elon Musk is amazing in terms of being an entrepreneur and really caring about the world and stuff like that. He will not be able to compete when Volkswagen and Audi get their stuff, because these companies have infinite amount of money, right? Volkswagen is one of the most probably is the most richest companies of all car manufacturers. Like Nissan being on number 10, Nissan, right? Volkswagen is probably, and Volkswagen owns Audi as well, so that tells you that too. So their development, research and development for battery technology, utilizing the quantum computing to figure out all the molecular structures and how to squeeze the most out of the, you can look at that as well if you want to. You will have 5 gigafactories producing the batteries and the cars. That's going to be really interesting when that thing hits the market. So, do you think they're hiring? Well, of course they're hiring, right? If they're investing $4 billion into development of something they don't have, they need people who understand this, right? And that's what they asked in the interview. Just like they asked that one time at the research facility at Excellence, like we just interviewed 150 useful graduates. Like, yeah, great. I know how to compute the flux. When we talk about flux? Today. That's the equation that they asked at the interview. If you want a serious job, right, then you need to know serious stuff. It's not just C's get degrees. Yes, they do. Do they get jobs? Not necessarily. Do they keep the jobs? Most likely not. Gotta know the stuff. Sorry. To burn your dreams. Guys, 50% of the lecture done. Let's go. The important part. Circulation and flux of a vector field. I just mentioned it, right? Let me just point out over here. Let's use orange again. Vector field. Example. Rotational. Vector field for electrical motor. There you go. And then if you wish to work and have a good job, you will go and look it up, right? Because we did you will just use this example over here, and you will put the minus sign right there in front of vector field. There's your rotational field, and you will go from there. Yay. Okay. Circulation and the flux. We'll go with the circulation first. Let me put that in blood over here. So circulation will introduce 2 new concepts. Flux will introduce 2 new concepts. And then we're done with lecture. So circulation is to be calculated in a 2D and a 3D fashion. So we start with a definition for circulation. Let F be a continuous vector field. Guys, in the future, vector field is just going to be capital VF because it's going to be everything from now on. On a region D in R3 and let C be a smooth closed oriented curve that has a lot of information in D. So the circulation of F on C is the line integral F dot T ds. Guys, this T ds is actually your R prime dt, but we'll write that later. Where T with the hat is the unit vector. Where T is the unit vector tangent to C, consistent with the orientation. This has a lot in it, but it's at least the first out of two concepts for circulation. So let's talk briefly about these things. First off, we see that we are in a 3D space. We also see that we have a tangent vector come back to our lives, which means we better know how to compute the tangent vector, and the tangent vector is a magnitude of R prime divided by, R prime divided by the magnitude of R prime, right? So that's the conversion that we are getting, that we need. We know this conversion from before, so obviously. So circulation. First of all, circulation of, like, what do you have as a concept in your head for the circulation? Like, you know that you have a blood circulation, right? What does it mean? Like, what is the, I don't care about math, but just tell me the words, yes. Path that something takes.
Covers the whole area.
Covers the whole area. Circulation of blood, what does it mean? Or circulation of water in the nature, like, what would that mean? It repeats. You're getting much closer to where I actually want to be. That's great. Flow circle. That means it's closed loop system, guys. Right? You don't spew the blood on each day and get the new blood in, right? That doesn't work, right, for us. I don't know what's happening with the story of the vampires. They drink all this blood, where it goes. Anyway, not efficient, right? The trick is that you have the closed system. Now look at the conditions. You have the vector field, fine. C be a smooth, closed, oriented curve. Great. Smooth. That means it has the derivatives, it's continuous, it's nice, right? Smooth. Things that have cusps and spikes, they're not differentiable, but they're not smooth because they have sharp edges, right? Smooth things don't have sharp edges. So when you say smooth, that means it doesn't have any sharp edges, turns, or cusps, or anything like that, so you're not going to cut yourself on it, right? So it's smooth. Like silk. Not a paper, right? You know, the paper cut is worse than a knife cut, right? That's always like that. So now what we have is the oriented. That means it's parametricized, right? Because when you do parametric equations, what do you get for free? You get orientation for free. Now, what is that orientation telling us? It's telling us in which way the motion would be if you are to put a particle on that path, right? So you have some curve C, and you drop a particle on it, or an ant or something, and it's going to go in a move in a direction of parametrization will show which way it's going to move. So it's a closed loop system. It's smooth, right? Which means differentiable, continuous, all that cool stuff. And then oriented, meaning it's parametricized, so we have parametrization there. Then we go here, and we see that the circulation is a measurement of how much something rotates, circulates, how much it moves in a direction of the tangent. So you are familiar with the tangent line in your Calculus 1 class. Calculus 1 class, they say you have a function and you have a point and you can calculate the tangent line, and if you ever asked why and how in your class, you also know that the tangent line is 90 degrees to the curvature and all of this cool stuff, that it's added as well. What have we done to improve on this in Calculus 3? Well, we said that your function f is now going to be parametricized, which gives you the motion. And then when you have a tangent line, the tangent line becomes a vector. So now you understand that if the roller coaster is to derail here, it will be launched along the tangent vector. If you have a skier or a skateboard or a bicycle or a motorcycle go on a hump, they don't launch from here, right? They launch from there. They don't launch even from the top. You launch from there. So now that your surface is parametricized, that means that the motorcycle came from this end, right? It's going to go whee and go that way. So the tangent line shows us not just how fast, but also in which direction things get launched. So now, when I multiply that with a vector field, there is a wind factor, there is a lot of this stuff. Parametricized on a ds, because this is all delta S parametrization, right? We move on from there. However, T ds is converted into r prime dt. R prime of t dt, right? So that conversion was given to us earlier. So now we are able to convert our line integral, which was f dot t ds, into c f dot velocity, or r prime, of t dt. I'll just put also r prime over here. So, oh, no, not velocity, sorry, r prime. Velocity is the magnitude. Sorry. There we go. Velocity is the magnitude of r prime, it's just r prime. All right, so example. Let's find some example. Well, actually, no, we have to do the two examples they give us because they are very educational. I actually have to use these two. So I have a unit circle. Well, that's smooth, right? It's oriented counterclockwise, and you can do parametrization, which is cosine sine. So everything is cool about the unit circle. I want to calculate circulation along the unit circle, but for two different vector fields, for a radial and rotational, right? So I'll have two different vector fields. So C unit circle, meaning when I do parametrization, I'm going to get that my vector r of t is cosine t sine t. Right? The radius is 1, r, right? Is 1 because it's a unit circle. From where I can immediately get the r prime, because I will need that, as negative sine t cosine t. So that's the orange parametrization. Now I want to consider two different vector fields. Part A is going to have radial vector field given by f equals xy. So that's our radial vector field. And then part B, I will consider rotational vector field given by standard negative y x. All right, so let's go do part A. So I have my rotational vector field. I have my function A, so I can plug everything in. Oh, I keep forgetting to write this because I know it, and then t has to be from 0 to 2 pi because I want the full circle. That's a part of parametrization. All right, our vector C of the vector field dotted with t ds is going to be converted into vector field dotted with r prime dt, and all of that stuff now is integral 0 to 2 pi because we are on a unit circle. And now we go we chase all of the parts we need. So x is given with x component, so that's going to be cosine t times, and now we need dx, which is negative sine t, plus, then we do the y is sine t, times we do the r prime cosine t, and all of that dt. Well, I hope you see it 0, because you're integrating a 0. Right, you have sine t minus sine t, that's a 0. Boom, 0. Does this make sense? The answer to that should be hell yes, if you actually spend time learning what the radial field is. Radial field is you have a source, and it shines out from that source. You have infinitely many of these vectors all going out. Just look at any kid's drawing of a sun, right? If you ever encounter a child drawing a sun, explain radial fields. Right. They have a two-dimensional radial field drawing over there. Is there any rotation here? No, because this vector has the one on the opposite side pulling in the other direction. This does not rotate. So circulation on that unit circle is 0. It's not spinning. Bueno? See. All right. Now, if we do the rotational vector field, we better find something. Part B. Same spiel. F dot dot ds, which is the f dot r prime dt. And now what we have? Well, we start with negative y, 0 to 2 pi. So what's negative y? Negative y is negative sine t times dx, which is also negative sine t, plus, you will see this is going to work out to be cosine t times cosine t, and everything dt. What you are integrating is 1 dt for a total of 2 pi. Now you ask yourself, does this make sense? And the immediate answer should be hell yes, because the tangent vector at every point of the unit circle is making this rotate consistent with the orientation of the circle. The parametrization for the unit circle that we picked was cosine sine. That means the orientation is counterclockwise. Do we see that these arrows are trying to turn it clockwise? Right? Each arrow helps the other arrow to spin this. Do we all see the spin? So circulation will measure that. Rotational fields have circulation, radial fields don't. Now, these are two extreme examples. You are going to deal with anything and everything in between these fields. So certain fields will have 0, right? But some circulation is there for vast majority of the fields. And all I need to do, and I'm not going to spend time on doing that, is to add a z component into the mix to give you the throw-dimensional circulation of the field, where you just put in a z, you have one more extra component, and then you ask yourself if there is circulation. Is there circulation at the orbit of the planet around the sun? Hell yes, right? Is there circulation on the surface of the sun? Looking at the UV radiation it has? No. Very good. No. Why? Because sun is a radial field when it comes to UV radiation. It radiates energy everywhere equally, right? So there is no circulation in that part. I haven't asked if the sun is spinning. Note that. I'm not asking if the sun is spinning. I was asking about radiating UV radiation, which, when it hits our atmosphere, gives us heat on the planet, right? So that's that part. So very easy to just add z component to everything we calculated before on our example. Well, two examples. So you'll just have, this equation, guys, is dimension free. You can do this in 16 dimensions. That just means you'll have 16 of these to multiply. That's what the, and 16 of them to add, obviously, right? Oh, sorry, 16 of them to add, you still multiply 2. But 16 of the components to add. So whether it's a 2D or a 3D, right, your vector field will have 3 components or 2 components. And that's the same for R. So we don't have to spend time going crazy calculating that. Don't worry, there's enough trees, we can build an arc. Just relax. We can extend this class to 4. No? All right. Flux. Flux and call it a day. For lecture, obviously. Is there an exam tomorrow?
Yep.
Oh, I hate you all. Like collectively. It's so much fun talking about these concepts and then you all exam. Just you had the choice. I was like, what's wrong with you? You should check that out, guys. It's really. We have a chance not to have an exam, and you're always like, yes, we do want the exam because. Flux. I guess when they fixed the air conditioning, they removed all the fans. It was really interesting a week on summer one. No air conditioning anywhere. So we brought in 13 fans into the classroom. Actually, some students brought in their fans, and college-owned fans were already in.
That was our class.
Was our class?
Yeah.
I thought it was summer one. No? Oh, it was our class. Okay, that was our class. I see, it was so long ago. So it was our class, right? So that fan.
Yeah, I brought my own.
Yes, you guys brought our fans. You brought your fan. We had 13 fans that day. And then they got the message and they finally fixed it next week, right? It was week 2, right? What is flux? Well, think of that fan, right? If you stand on the side of the fan, you don't feel the wind that the fan is pushing. What is wind? Wind is all of that vector field, right? All the forces that are pushing air molecules forward, right? So it can move dust from one point to another. If you stand on the side of the fan, i.e. not facing the surface area of the fan, you are not feeling anything. If you stand directly in front of the fan and let the fan air hit you, then you feel it. Flux computes the amount of stuff that is radiated through that area of the front of the fan. So what do you have? You have this vector field of all of the vectors pushing perpendicular to the face of the fan. You want to create a fan that fans out everywhere? Make those blades, like the front of the blade, make that curved. It's going to radiate everywhere. You want to focus it, you put the face straight, it will go straight out. Another example of this would be your headlights on the car, right? They want to spread that, right, as wide as possible so that you can see animals and stuff and stuff on the road and so on. They don't want to make it high because it's going to blind the next person driving towards you. But then you have low and high beams, and the high beams allow for the everything, right? Which is why you shut them off, hopefully, as someone is approaching. So, what is flux? Flux is amount of stuff. And I say stuff because it could be wind, it could be water, it could be light, I don't care what it is. So amount of stuff that gets radiated perpendicular to the surface that it's radiating stuff out. Now, when you look at the sun is a ball, right? Contrary to what flat earthers believe, because they have a flat sun, I guess. I hope, I don't know. But even though when they have a flat sun, the flat sun will do the same thing in 2D. All right? So what do we have? We have a surface, right, which has an area. And then now, clearly, the normal vector is the one that plays the role. So for circulation, you have the tangent vector. Hello, chapter 11.9, right? You remember the tangent vector and the normal vector calculations? Yeah, it was there, right? So now we are using it in a situation where we actually have to create stuff. So the amount of light, the amount of energy, the amount of radiation, the amount... So this is directional stuff, which is why if you want to have a serious research job, well paid, 6 digits and up, in a lab that does alternative energy research, well, clearly they're going to ask you to be at least able to calculate the basic idea, and then go there and take a look at the Star Wars and Star Trek things they're developing, right? So now let's talk about the flux. The flux is going to have the continuous vector field. It's going to have the smooth oriented curve, right? And all of that stuff that does not intersect itself. So you can't have number 8. So smooth oriented curve that does not intersect itself, and then you have the flux. So let's put the specs first. So this is definition. So vector field Fg is continuous on R in R2. Let C, which is given as a parametrization of x of t, y of t, there we go, for t trapped between A and B, be a smooth oriented curve, be a smooth oriented come on, There we go. Curve in R that does not intersect itself. If you're ever going to ask me why, I'm just going to say you've never seen a propeller in the shape of a pretzel. It doesn't work. So the flux of the vector field F across C is, and here is the normal vector, F dotted with the normal vector N, ds is equal to, and now we have our f of t. Now this is backwards. This is called divergence. It's in the next lecture, tomorrow. We'll call this stuff. We'll name it. So vector n is the closed curve with the counterclockwise orientation. The n is called the outward normal vector, and the flux is called outward flux. So yeah, I can write that in orange, I guess. So when n is normal vector with normal vector on counterclockwise R, it is called outward normal vector, and vector field is called, sorry, not vector field, and the flux integral is called, and the flux integral is called outward flux. There we go. The formula to calculate flux is right here, and that's what they asked at the interview, to calculate the outward flux. So, well, let's calculate outward flux for our two candidates. Right, we have a candidate, the rotational field and radial field. So, part A, well, let's set up the scenario. So again, we have C to be unit circle. Giving us all of the specs that we know. R is going to be cosine t, sine t. See, now orientation is important. You have to put cosine first if you want the outward flux, right? Otherwise, it's an inward flux if it's splits different way. They don't say it, but it is what it is. Negative sine t cosine t, and for the first time today, I will immediately say that t is between 0 and 2 pi because we want the full circle. Part A, our vector field is going to be, okay, which one is this? Radial or rotational? Radial, thank you. So this is radial, and we have the flux integral, so f dot n The S is going to be integral a to b of f y prime minus g x prime dt. We just chase these things around. 0 to 2 pi. F is given as x, x is cosine t. Y prime is given as cosine t. Minus g is given as y, which is sine t, times negative sine t dt, which is equal to integral of 1 dt, which is 2 pi. So flux of the radial field is 2 pi. Does it make sense? Well, yes, that's the purpose of the radial field, to radiate stuff out. How does it radiate? Perpendicular to its surface. Good. Radial field, there we go. Yay. Stuff is coming out of the there we go. Now we have the rotational, and we are expecting what for rotational? One big fat 0. Thank you. So we have integral 0 to 2 pi. Our f is negative y. So this is supposed to give us negative y, negative sine t, times cosine t minus, is it times cosine t? Times negative sine t times g. Okay, negative y, that's negative sine t, times x prime, no, times cosine t, good. And then we have minus, now we have what? We have x is cosine t, times negative sine t. There we go. dt. This is the integral 0 to 2 pi of big fat 0 dt gives us 0 dt, which makes sense because nothing radiates out, this thing spins. So flux is 0. Radial field, flux is max. Now they're going to ask you to calculate all different types of things. You just go around and you chase your vectors. So there are circulation problems. We're going to go now into review for the test. There are circulation problems here and flux problems. They only give you 4 to practice, but this stuff will come back. And then also you have a whole bunch of problems online, so keep practicing. That's it. Bye.